Let's begin. Okay. In 3.2, we're going to look at the idea of differentiability. Whether a function has the ability of having a derivative or not. In other words, there may be some places where the function f prime of a fails to exist. There are places, situations where f prime might fail to exist. F prime being the derivative function. And why is this not working?
Oh, there it is.
There we go. One place where it might fail to exist is when a function has when the original function has a corner, like in the absolute value function. Now, I think we talked about this a little, but let's just talk about the slope right here on the absolute value function. Negative 1. Slope is equal to negative 1. How about right there? Negative 1. And right there? Negative 1. All the way down this line, all these slopes are negative 1. How about over here? And 1, and 1, and 1. Now, as we get to that very point right there, the right-hand derivative, the derivative as if we're coming from the right, is equal to positive 1. The left-hand derivative is negative 1. And because the derivative function is defined as a limit, what we end up having is two limits that do not agree. The two limits don't agree. When the right-hand limit and the left-hand limit don't agree, the result is that the limit does not exist. Since the derivative function is a limited function, if the limit doesn't exist, the derivative doesn't exist. So we say that in this situation, f prime does not exist at x equals 0. Now this is going to happen whenever the graph ends up having a corner. We always end up having that situation where the two-sided limits don't agree, and then therefore the limits, the overall limit that makes up the derivative doesn't exist. So no derivative function at corners. Near corners, yes. At the corners, no. Yes, Ian?
Even though a parabola doesn't have a corner, aren't both sides opposite or not the same?
You're talking like at the right there?
Yeah.
You're saying that all of these values are all these slope values are negative?
Yeah.
All these slope values are positive. But those negative values end up getting closer and closer to 0 on the negative side, and the limit is 0 on the negative side. All these slope values are positive, but as we get closer and closer to 0, all those slope values getting closer and closer to 0. The two limits both end up equaling 0. At that moment, the limit does exist, and we are differentiable at that point.
Okay.
When we say that the derivative function doesn't exist, we say that the original function, is not differentiable at that point. Here's another place where a derivative function would fail to exist. And this one is called a cusp. C-U-S-P, cusp. This is similar to the point that Ian just made. Except in this case, as we get closer and closer to the cusp, indeed all these values are negative. Negative slopes all through here. But what happens as we get closer and closer to 0? That that curve, that the slope gets greater and greater. -1, -2, -5, -100. The left-hand derivative on that side ends up being, as it approaches 0, -infinity. It becomes vertical. What about on the right-hand side? Positive, positive, positive. Positive and more steep as we get closer and closer to 0. The right-hand derivative in this case ends up being positive infinity. Last time I checked, negative infinity and positive infinity don't equal each other. The limit doesn't exist, so therefore the derivative doesn't exist. Yes, Lucy?
Will you draw the derivative for that one?
Sure. The derivative function for this one, okay, it's negative on this side, and as we go on and on and on, it's getting flatter. So it's essentially getting closer and closer to 0 as we go on. But as we get closer and closer, the derivative is closer and closer to 0. As we approach 0, the function's going down like that. The slopes are getting bigger and bigger and negative. And then over here, we're positive and getting flat, so we're approaching 0. As x approaches 0, the slope function is going up like that. So again, the idea is this is my f, this is my f prime. And it's clear to see that those two values, the value of f prime as we approach 0 have two different limits. That limit doesn't exist. Therefore, the derivative doesn't exist at 0. So there's the second place where derivatives will fail to exist. Corners and cusps. A third place where a derivative would fail to exist, where the tangent line slope is vertical. Where the tangent line is vertical, I should say. If I were to draw the tangent line for that curve at 0, we get a perfectly vertical line. What do we know about the slopes of vertical lines?
Undefined.
They are undefined. You know what? I think I'm going to do the same thing that Lucy asked. What does the f prime function look like here? Because for all the other points, guess what? There's derivatives, aren't there? Okay. It's all these slopes are positive, and all these slopes are positive. So I'm going to only be in the upper. I'm going to only have positive slopes. It looks to me like what I'm doing is I'm going here, and as I get closer and closer to 0, I'm getting more and more steep. So my derivative ends up having that kind of behavior. So I get closer and closer to 0, the line gets steeper and steeper. And as I'm doing this part, I'm still positive, but I'm very steep, and then I start going towards 0. So the derivative function of that curve would look something like this. And as you can see, that f prime function definitely is not defined at 0. Are we good? Danielle?
So on the f(x) graph, both sides of the function are both approaching.
On the f of that, both sides of the
Both sides are approaching either x or negative. I mean, infinity or negative infinity. That one.
the slopes here are positive and getting bigger and bigger and bigger because the slopes are steeper and steeper and steeper.
Oh, as they're approaching 0.
As they're approaching 0, the slopes are getting bigger and bigger and bigger.
They're approaching infinity.
Right.
Okay.
And right at 0, they seem to be straight up and down, but just as we move a little bit off of 0, that's very steep. Nearly vertical. Just after 0, on the right-hand side of 0, these slopes are very, very steep. They're very, very, very large. And that's why we have very large values of y here. And as we move away, they flatten out.
Okay.
Are we okay with the third place where limits fail to exist? Sorry, where derivatives fail to exist?
Yeah.
2 people got it. Everyone else?
Yeah.
All right. A third place where limits fail to exist are at discontinuities. If a function is not continuous at a point, their derivatives don't exist. Now, we said derivatives fail to exist when there's not agreement between the 2 one-sided derivatives. Looks to me for this function f, all of these slopes are 1. 1, 1. Sorry, all these slopes are 0. 0, 0, 0, 0, 0. Everything's 0 here. It seems to me like the right-handed derivative of this function is 0. Are we good? But what about the left-handed derivative? Yeah, 0, 0, 0. But guess what happens there? When the function doesn't exist, the left-handed derivative doesn't exist. The absence of that point right there makes the left-handed derivative non-existent. If you don't have one of the 2 one-sided derivatives, you can't have agreement. The left-handed limit, the left-handed derivative fails to exist because of the absence of that point. So, 4 places where derivatives fail to exist. Corners, cusps, vertical tangents, and discontinuities. Okay, I want you guys to take 20 seconds, and I want you to let's say the people on the window side, I want you to explain it to the person on the other side. 20 seconds. Go.
Go ahead, buddy.
Draw pictures.
Which one? Yeah, so, alright. First one, slopes -1. That one's 1, -1, 1, -1. Then they meet. It doesn't work out. Since 0 is yeah, that's probably what it's about.
Okay, 20 seconds over. Switch.
No, but it does not exist. No way have a graph to both sides. They're not
Stop. Okay. By the way, we're going to do a lot more of this. I'm feeling, as I've been looking at like why we're not achieving as high as I think we should, I'm realizing that I am too conceited about the importance of my own words. Who else am I going to blame? Then I'm a victim. I'm not going to be a victim.
You're a victim.
I'm not a victim.
You're already the victim.
So, let's talk about this piecewise function. And we're going to talk about another way of looking at can a derivative exist in this particular situation. We say the function fails to have a derivative if the 2 one-sided derivatives don't agree. Is that true at in this particular instance? They agree?
They agree. No. Yeah, because they're both positive.
Right, it goes from 0 to 4. How is that
When x is greater than or
They're both approaching.
There's no holes next to the cube.
My answer is no holes.
There's a vertical.
It's not because the left hand limits are.
We already know it's not. We're arguing on the right hand side.
Is it because the slopes don't agree?
Do the slopes agree?
No, because one will always be 4 while the other one is approaching 0.
Yeah. The slopes don't agree.
Do the two-sided derivatives agree? Now, if I allow you to use the shortcut, well, first of all, we know this. By inspection, what is the slope of the right-handed derivative? Sorry, I misspoke that. The slope of the right-hand derivative. What is the right-hand derivative? It's 4. Everything to the right of 0 has a slope 4 because it's a linear function. What about the cubic function? 3x squared is the derivative, but if I drew up the typical cubic function, what would you say is the slope at 0? 0. So we've got a right-handed derivative that's 4. We've got a left-handed derivative that's 0. Does 4 equal 0? No. Conclusion. The derivative doesn't exist. Why? Because the two one-sided derivatives don't agree. All right. So the right-hand derivative is 4, the left-hand derivative is 0. The function is not differentiable at 0. Is it differentiable other places?
Yeah.
Sure. All on the right-hand side, all those slopes are known. They're 4. And if we know the shortcut, all of the derivatives on the left-hand side, they're all findable. 3x squared.
So what you're saying is the left-hand derivative is 0 when it's
At-
or approaching 0?
When you're approaching 0, the left-hand derivative is 0.
Okay.
There's a better drawing, I think, of that than that graph.
Okay.
This part of the graph, on the left-hand side, those slopes are approaching 0 as x approaches 0. All of these on this side, they're all 4.
Okay.
They don't agree. All right. Now, is this function continuous, by the way?
Yes.
Why?
Because it doesn't really have any points.
Because the left hand limit and the right hand.
They're both 0. The limits.
At the point where the two piecewise functions come together, they both have the same value, and that is 0. So this function is continuous, but not differentiable at 0. Can I say that again? This function is continuous without being differentiable. All right. Okay. In general, though, the functions that we're going to deal with in class, the functions that we mostly deal with, they're differentiable wherever there isn't a cusp, there isn't a corner, there isn't vertical tangents, and where they're defined. So whenever we look for a lack of differentiability, it's one of those 4 things: discontinuity, cusps, corners, and vertical tangents. Right? Otherwise, those functions are differentiable on their domains. Okay? In general, these graphs that have derivatives everywhere, they are unbroken, continuous, and they are smooth. The corners and cusps are the things that create the non-smoothness. I've got a better definition for smooth, but you're not ready for it now.
I'm smooth, yeah, smooth.
Okay. A couple of other things. This is a much bigger deal before we had calculators. Differentiability implies local linearity. Take a step back and explain what that means. It means that if I zoom in on any curve, Even if it's a really curvy curve. If I zoom in enough, it's going to appear like a straight line. Any zooming in on any curve, if I zoom in far enough, the function appears, at least in that very little space of time, it appears linear. And that little space where it appears like it's a line, that line will have the same slope as the tangent line slope.
So if you're like on a test and we're just like going like, keep zooming in.
Well, I can show it to you.
That's kind of like the average rate of change thing, isn't it?
Gosh, does that analogy work or not?
Just as you're decreasing the step size, you just get closer to.
Yeah, as I decrease the step size, I end up getting something that's looking more and more linear. Okay, yeah, I will go with that. Okay, so when we zoom in, the curves appear to straighten out. And there's an example of this. Here's a curvy curve. But if I zoom in on it, oh, it still looks curvy, doesn't it? Maybe all I need to do is zoom in more. So when I zoom in on this area only, it really appears like a straight line. And this was really important in the old times when it was really difficult to make calculations on curves. But we exploited the fact that I may have a difficult time finding things going on with that curve, but I certainly can, if I can find the derivative, I can certainly say for a really short period of time, it acts like a straight line. And the straight lines make really good estimates of what the curves would be doing. Yeah?
Can you go back to the last slide for a second?
There. So, over very, very short spans of times, curves can appear like straight lines. And those straight lines have tangents that are relatively easy to find because we have the ability to take the derivatives. All right? Go ahead. The microphone will have picked up every single one of those patterns. It's okay. All right.
Are we recording right now?
Yeah.
Hello.
All right. Now, I'm going to show you something. I'm going to talk about what's called a numerical estimate of a derivative. Now, we know that we have this idea of a derivative as this being is f of a plus h minus f of a over h. And as h gets really small, as h approaches 0, we get a derivative. But one way to do this is that say, not when h gets to 0, but if I just put in a real small value of h, guess what I end up getting? I get a reasonable guess at what the derivative is. It's not as good as doing the algebra, but for very small values of h, this quotient gives a good approximation of the value of the derivative at a. What's even better than doing it at a, or using this one, is to use this particular difference quotient. Not keeping a as one end of a little secant line, but making a the middle of a little secant line. I want to demonstrate this real quickly for the x squared function. For example, let's say f is equal to x squared and a is equal to 1. and I would like to know what is f prime of A? What's a good estimator of f prime of A? Well, for a small value of h, maybe 0.001, we could say this is approximately 1.001 squared minus 0.999 squared over 2 times 001. Essentially, I'm saying, let's just take a really thin slice of h, let's go a little bit below, a little bit above, and what I'm going to get? A difference in y's divided by how far I moved in the x. Exactly? If you put that in your calculator, how close do we get?
Oh, I got
Exactly?
yeah. That's crazy. Wow.
Is it supposed to exactly?
Yeah, it's approximate. I mean,
I got 2.
so you
Did our
get
calculator
you got 2.
round?
Okay, it's within the range of error, and it rounds it and gets
Yeah,
two.
I'm guessing like 0.0.
Okay, this function, this idea of estimating the value of a function by taking really small values of h on either side and plopping the value in the middle is already built into your calculator. It's already built into your calculator. It's built in your calculator in 2 different ways.
What's built in? The derivative in this numerical.
What's called the numeric derivative.
The end derivative.
It's built in your calculator in 2 ways, and I want to show you both ways.
Yeah.
All right? Here's the easier of the 2 ways. I go y equals. I put in a function. I'm doing, by the way, exactly the example that we just did by hand. I graph it. Under the second calc menu, there is a synonym for derivative. dy, okay, remember, we don't say the over part. I don't know why. dy dx. If I say calculate for me the derivative, I hit 6, and then I put in the x value.
Of
1.
We wanted the derivative when x was 1.
Well, let's say
So-
It says dy dx is equal to 2.
Why do we even need it? We got calculators.
But wait,
Is there more?
sometimes you don't want to have to go through the graphs. So there is a second way of getting at the numeric derivative using this, again, h equals 0.001 slicing stuff. And it's under the math command. If you look under math, and look way down in the bottom, there's this command called nderiv, the numeric derivative. Now, the syntax or the order that you have to put things in for nderiv is a little bit harder, but it works like this. You start with an expression, the function that you want to take the derivative of, x squared. Oops, I missed my caret. There, x squared, comma. The second thing you have to put in is the variable that you're taking the derivative with respect to. We're only been, no, variable.
Oh.
We are taking the derivative with respect to x. Remember it was dy dx on that other screen? With respect to x. Yeah.
Okay, hold on, I'll let you finish.
The last thing we put in is the place that we want to take the derivative when x equals 1. It is the variable that we are taking the derivative with respect to.
My calculator is a different.
Okay. if you have an upgrade to the operating system, okay, if you have an upgrade to the operating system, your screen will look different when you say numeric deriv. You get this really cool thing, and it's got d squared, right?
Yeah.
A line there, right?
No,
Wait, there's a parenthesis.
There's parentheses. Here, you can look at mine.
Yeah, let me look at it. But it gives.
Here you go. It's right here.
Right.
I was doing something, I just added it.
Okay. Okay. Parenthesis, line,
What?
and then
Whatever.
it probably doesn't say x, does it?
It's a square.
Hold on.
There's a square there.
I'll come up there. Looks really great.
Hold on.
Just move left and right. There's a square there for.
Hey, you.
Okay. Okay. It starts.
There it is.
Okay. Okay. Eventually, all of you are going to get this upgrade if you have an 84.
This is an upgrade.
83 plus.
I got an 84.
Okay. If you have the operating system upgrade, when you hit end deriv, you get this. And essentially what's going on is that the little dotted boxes are things that you fill in. When we take, remember that we did the synonyms screen, like all the different ways we can say derivative? The very last one was d over dx. When we put the x there, it says we're taking the derivative with respect to x. This x here is the equivalent of that x bit right there. In this big box, this is supposed to be parentheses, is what we're taking the derivative of, x squared. This box is the equivalent of that area in the end deriv command. As soon as you put x here, x appears in that little square there. This is where we say where we're taking the derivative. Oh, it should be 1. And that square here is equivalent to that area there. So the new calculator upgrade shows you symbolically what things you're supposed to put where, as compared to the old way where you had to remember it's expression first, variable derivation second, and place of derivation third. All right? Yeah.
Okay, so in stuff like this, like, 'cause whenever you do x on your home screen, it like if you're just doing like x plus 2 and you stored x as 1, it would like obviously store it and keep it stored. But when you do it in like stuff like this, it doesn't use that value.
It doesn't
Okay,
use
that's
that
what I
value.
was wondering.
We are temporarily setting the value of x to be 1 in that
Yeah,
instant.
because of
That's a very good question. Very good insight. It overwrites the value. I think it may even overwrite the value of x.
okay.
So if I went like
So
right
did
now,
it just
if
store
I asked
it probably?
what the value of x is right now,
Oh, okay. So
if I said what's the derivative of x squared, I can't get back to my end deriv. How come? Okay. So if I change that to, I'd like to find the value of the derivative at 2. I bet you if I say x now,
oh,
no.
okay. So it's just exclusive for that.
All right.
Should we
So-
get a question?
I think the upgrade is cool. There's the visual aspects are nicer. There is a downside to the upgrade, and that is the one thing that I found that makes me angry when I do the upgrade. When you're typing in a very long formula, it will scroll off the screen.
Oh, like that guy.
Yeah, and so you can never. And so for long things that you're entering, you can't see everything at once.
You can switch in between the old and new software if you go to mode. Go to classic.
Really? Okay, then that may be worth it. Okay. Well,
You can go to classic.
all right. Good to know.
So,
All right, I did not know that. Thank you.
Learn something every day.
I learn many things every day.
yeah.
Okay. So again, the end derivative in your calculator is built upon this formula. Built upon this formula, and it forces the h value to be 0.001. So it's not doing anything that's all that incredible. It's a formula. It's using a small enough value of h. All right. And we don't need to do that example. Okay. The one thing to note here about the end derivative function, it's just using a formula. It doesn't look to see whether a function has a cusp or a corner or a horizontal tangent, or sorry, vertical tangent. It just plugs the numbers in and sees what it gets out. So in some cases, the end derivative will give you a value of derivative when the derivative really doesn't exist. For example, I could ask the calculator, please tell me the value of the derivative for the absolute value function at 0. I could ask it to do that. Now, what is it going to do in order to do that? Oops, I am not right here. Missing a parenthesis, right?
Around there.
Okay.
And then an end parentheses.
Yeah, although it'll let me get away without having the last one. But I could ask, what is it? What's the absolute value? What's the derivative of the absolute value at 0? We know, because of cusps and corners, that derivative doesn't exist. But what is it going to do? It's going to say, let me go a little bit above 0, let me go a little bit below 0, and tell me what the slope is between those 2 points. It's going to tell me 0. Oh, sorry, put down the pen. It's going to tell me 0. It's going to lie to me. Because all it's doing is running it through a formula. So in the cases where it can lie to you, you need to be smarter than your calculator.
I'll try.
All right.
Godspeed.
Okay. Next point. If I tell you a function is differentiable, if I tell you a function has derivatives for its entire domain, embedded in that statement, something that you can take to the bank is that the function must be continuous. If the function has a derivative at x equal a, it is implied that the function is continuous at x equal a. The converse of this statement is not true. The converse is, if a function is continuous, does it have a derivative? Not necessarily. But if I say something has a derivative, it is implied that the function is also continuous. In fact, if I were to say a function is continuous and differentiable, I'm being redundant. I need only say a function is differentiable, and then you know automatically that it's continuous. All right. Now you go on to the next screen?
Yep.
Yeah? All right. Okay, the converse is false. Because a continuous function may have a corner or cusp or vertical tangent, and therefore not be differentiable. I think we're heading into the home stretch here. Let's remind ourselves of what the intermediate value theorem was, and then we'll talk about the intermediate value theorem for derivatives. If a function is continuous, we said the intermediate value theorem allows us to say the function must take on every single value in between two y values. The old intermediate value theorem said if this function is continuous and it goes from f of a to b f of a, or b f of b, that there exists a c such that for every value between f of a and f of b, there exists a c such that f of c is equal to that value. So if this is 5 and this is 10, you said, hey, does this function ever give a 7? I'm guaranteed that there's at least one place where the function gives a 7. And that c is in that interval from a to b. Here's the intermediate value theorem for derivatives. F prime, F prime. If a function's differentiable, we also have this quality, that the derivatives have to fill in all the gaps in between the two values of the derivatives as well. If a function goes from a 0 slope to a 1 slope, somewhere in between there, guess what? The slope is going to be 1/2, or 1/4, or 1/3. If a function is differentiable from these two values, from a to b, and the function was 0, had a 0 slope there, and a slope of 5 here, somewhere in between there is going to have a slope of 4, or 2, or 1/2. All the values of the slopes have to fill in if the function is differentiable.
That's like a good check for
Ian?
Is the second graph that you drew, is that the graph of the
Original function.
or the derivative?
This is the original function graph.
Okay.
It has a slope of 0 here, a slope of 5 here. Somewhere in here I'm guaranteed a slope of some number between 0 and 5. Oh, here's another one. Here's the slope of -2. Here's the slope of +2. Somewhere in between there, I'm guaranteed is a 0. There's a slope of 0. At least one place there has to, if the function is differentiable. If the function is not differentiable, all bets are off. Piecewise. Piecewise. Here's a function. Hey, over here is here's a slope of -1. Over here there's a slope of 1. Am I guaranteed a slope of 0?
No.
Why not? Because this function isn't.
It's not
It's not differentiable everywhere on that interval. So if you don't meet that condition of differentiability, all bets are off. But if you do, if you're differentiable, you've got that extra quality that you can do it. No, we're still really far behind. We need to do 2 sections a day. We did 1 section today. We are not making good time. Yeah.
It says 1 through 12 and 1 through 25
11.
There it is. Okay.